Picture a garden sprinkler spinning on a summer lawn. Water arcs out in graceful, curving streams, painting wet circles on the grass. Now, imagine that same sprinkler whirling just as fast, but somehow shooting water in perfectly straight, laser-like lines that never bend, never curve, never acknowledge the furious rotation happening at their source. The streams stay locked to fixed points, north, south, east, west, while the sprinkler itself spins like a top. That would be magic. It would break reality. In November of 2025, astronomers photographed exactly that, but it wasn't happening in a backyard. It was happening in the vacuum of space, 400 million kilometers away, with a celestial object known as Comet 3I Atlas. On November 8th and 9th, 3 separate teams of skilled amateur astronomers, Christian Nebling and Gerald Buchner in Germany, Michael Jagger, Gerald Riemann and Rolando Ligustri, working from Austria and Italy, pointed their telescopes toward this interstellar visitor. They stacked their long-exposure images, a technique to tease faint light from the darkness, and all 3 teams, independently, saw the same impossible thing. Jets of material shooting outward from the comet's nucleus, stretching over 1 million kilometers into the void. They were perfectly straight, perfectly columnated, and perfectly fixed in their orientation, unwavering against the backdrop of distant stars. Here is what makes this impossible. We know with certainty that 3I Atlas rotates. It completes a full spin every 16.16 hours. This is not up for debate. And when something rotates and expels gas, basic kindergarten-level physics dictates what must happen. The gas should trace a spiral pattern, a fan, a smear across space as the source spins beneath it. Just like the garden sprinkler, the faster it spins, the more pronounced the curve. This is not complicated physics. This is Tuesday afternoon in your backyard. Yet the jets from 3I Atlas do not blur. They do not smear. They show no spiral structure whatsoever. They remain fixed, locked to some invisible framework that has nothing to do with the tumbling, spinning nucleus below. This has been dubbed the 12th anomaly of 3I Atlas. Not the first oddity, not the second or the 5th, but the 12th. This object has been throwing curveballs at astronomers since the moment it was discovered, and each new anomaly has been stranger than the last. But this one, this unblurring mystery, might be the strangest yet. Because if these jets are real, and if they truly remain fixed despite the confirmed rotation, then something about our understanding of comets, or perhaps about 3I Atlas itself, is fundamentally, catastrophically wrong. We have always assumed that interstellar visitors, however exotic, still obey the basic, universal rules of physics. Gas expands, objects rotate, rotation plus outgassing equals spirals and smears. But what if those assumptions only hold for natural objects? What if the rules change when the object in question was built, rather than born? If you're as captivated by this cosmic puzzle as I am, if you feel that chill of wonder and curiosity, then I want you to be a part of this investigation. Go ahead and hit that subscribe button so you don't miss a single development as this story continues to unfold. We are just getting started, and what we uncover next might rewrite everything. And let me know in the comments where you're watching from right now, what time it is in your corner of the world. I read every single one. Let's talk numbers, because numbers are the one language that doesn't care about our theories or our biases. They simply are. When volatile ices on a comet's surface sublimate, when frozen carbon dioxide or water ice turns directly into gas, the molecules fly outward at a specific speed. For typical cometary ices, that thermal velocity is about 400 meters per second. Not fast by cosmic standards, but steady, reliable, and measurable. Now, apply that speed to the jets we're seeing from 3I Atlas. These features extend roughly 1 million kilometers from the nucleus. How long does gas traveling at 400 meters per second take to cross 1 million kilometers? The math is straightforward. 1 million kilometers is 1 billion meters. Divide 1 billion by 400 and you get 2.5 million seconds. That is roughly 29 days. Just under a month of continuous travel for a gas molecule to get from the surface of the comet to the farthest visible tip of these jets. Here is where the problem crystallizes into something undeniable. During those 29 days of travel time, how many times does the nucleus of 3I Atlas complete a full rotation? The spin period is 16.16 hours. There are 24 hours in a day, so that's roughly 1.5 rotations per day. Multiply that over 29 days, and the nucleus spins approximately 43 times. 43 complete rotations, while the gas streams outward to form these supposedly straight, unsmeared jets. Fiberglass about that. Every 16 hours, any active vent on the surface sweeps through a full 360 degrees, pointing in every possible direction relative to the stars. The gas it emits should follow that sweep, tracing out a spiral pattern like cream stirred into coffee, wrapped 43 times around the nucleus. But that is not what we see. The images show linear features, columnated jets that maintain a consistent orientation across their entire million-kilometer length. If you were standing on the surface of 3I Atlas at an active vent, you would complete 43 pirouettes in the time it takes for your breath to travel to the edge of visibility. Your breath should form a vast, spiraling disk around you. Instead, it forms a laser-straight line pointing toward a fixed direction in space, completely ignoring the spinning platform beneath. This is not how gas behaves. This is not how rotating sources work. Perhaps our velocity estimate is wrong. Maybe some process accelerates the gas faster. Even if we double the velocity to 800 meters per second, we still have 14 to 15 full rotations during transit. Still a spiral, still a smear. You would need velocities approaching tens of kilometers per second to reduce the rotation count to something negligible. And at that point, you're not talking about sublimation anymore. You're talking about explosive decompression. You're talking about rocket exhaust. You're talking about something else entirely. The audience needs to understand this is not a minor discrepancy. This is not measurement noise. The physics here are as fundamental as gravity. When you spin something that emits gas, the gas traces your spin. When 3I Atlas spins 43 times while emitting these jets, the jets should show 43 wraps of spiral structure. They don't. Something is maintaining their fixed orientation despite the rotation. Something is compensating for the spin. And if natural comet physics can't do that, we are forced to ask a terrifying and thrilling question. What can? Before we go further, you need to understand that 3I Atlas has been strange from the very beginning. This is not a case of one weird observation prompting wild speculation. This is a pattern, an accumulation of oddities stacking up like evidence at a crime scene. The object was discovered in 2024, classified as C2024-S1, the first interstellar comet detected after the now famous Oumuamua and 2I Borisov. Its trajectory immediately marked it as a visitor from beyond, following a hyperbolic orbit that originated somewhere in the vast spaces between stars and would eventually return there after a brief visit to our solar system. Deported from the start, something was off. Non-gravitational acceleration was detected early, subtle changes in its trajectory that couldn't be explained by the sun's gravity alone. In comets, we expect this. Outgassing can produce thrust, little rocket effects that nudge the nucleus. But the magnitude and direction of 3I Atlas's acceleration didn't quite match the models. It was stronger than expected for its observed brightness, suggesting either unusually efficient outgassing or something else providing the push. That was anomaly 1. Then came the brightness curves, the way the object's light changed as it rotated. Comets typically show predictable patterns. 3I Atlas showed variations that didn't fit standard models, with reflectivity changes that suggested an unusual surface composition or geometry. Anomaly 2. Spectroscopy revealed compositional weirdness. When the James Webb Space Telescope pointed its infrared eyes at 3I Atlas, it detected a coma dominated by carbon dioxide, with an extraordinarily high ratio of CO2 to water. Normal comets, both from our solar system and interstellar space, typically show water as the dominant volatile. 3I Atlas seemed to be exhaling almost pure carbon dioxide, a chemistry more consistent with formation in an extremely cold environment or with some other unusual origin. This high carbon dioxide to water ratio became Anomaly 3. But perhaps the most striking early anomaly came from polarimetry, the study of how light scatters off the dust and gas around the nucleus. In 2025, Gray, Benulo and colleagues published observations showing that 3I Atlas displayed an extreme negative polarization branch unprecedented among comets. The degree and nature of its polarization suggested dust particles with properties unlike anything in our catalogue of known comets. Anomalies 4, 5 and 6, depending on how you count the sub-anomalies. As observations accumulated through late 2024 and 2025, more oddities emerged. Trajectory refinements suggested possible close approaches to Mars, Venus and Jupiter, statistical alignments that seemed too convenient to be random. Its thermal emission didn't quite match models. Every new observation seemed to add another layer of strangeness, another reason to question whether 3I Atlas truly belonged in the same category as ordinary comets. The time we reached 2025, the list of anomalies had grown to 11 distinct features that collectively painted a picture of something profoundly unusual. And then came the 12th anomaly, the unblurring jets, the fixed orientation despite known rotation. If the first 11 anomalies raised questions, this one might finally provide answers. Because once you rule out enough natural explanations, what remains, however improbable, must be considered. Let's be fair to the natural explanations. Let's give them their due, because jumping straight to exotic conclusions without exhausting conventional possibilities is bad science. The first and strongest natural explanation for the fixed jet orientations involves geometry, specifically the geometry of the surface terrain and how sunlight interacts with buried ice. Imagine the nucleus of 3I Atlas is not smooth, but heavily cratered, a landscape of peaks, valleys, and deep, shadowed depressions. Now imagine that volatile ices are trapped not uniformly across the surface, but in concentrated pockets at the bottoms of these craters. As 3I Atlas rotates, most of the time these ice pockets remain in shadow, frozen and inert. But when the rotation brings them into direct sunlight for a brief period, when the geometry aligns just right, they sublimate rapidly, releasing a short, powerful burst of gas. This pulsed outgassing model could, in principle, produce discrete clumps of material rather than continuous streams. Think of it like beads on a string, individual puffs of gas separated by empty space. The nucleus rotates every 16.16 hours. If an ice pocket gets illuminated only once per rotation, it produces one puff every 16 hours. At 400 meters per second, that puff travels approximately 23,000 kilometers before the next puff is released. Over a million-kilometer jet, you would have roughly 43 such clumps, separated by regular intervals. If you stack multiple exposures taken over several hours, these discrete clumps might blur together in a way that looks like a continuous, straight jet. The individual puffs are all travelling in roughly the same direction, because they were all released when the source vent was pointing in the same orientation relative to the Sun. So even though the nucleus rotates between releases, each puff follows nearly the same trajectory, creating a columnated feature that appears fixed. This is clever. This respects the physics. This could work. We have seen this kind of terrain-controlled outgassing on other comets, most famously on 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft. The mathematics are straightforward and testable. High-resolution imaging should be able to detect this clumpy structure if it exists. If future observations confirm this with the predicted spacing, the crater geometry model wins. It would be a natural explanation validated by testable predictions, exactly how science should work. But here's the problem. This model works convincingly only for jets pointing toward the Sun, where direct sunlight is the trigger. The November 8th images show jets in multiple directions, including features pointing away from the sun, anti-solar jets, where direct illumination cannot be the trigger. You could argue for reflected light, or thermal lag keeping areas warm, but these are weak effects. Reflected light is diffuse and faint. Getting enough of it to drive significant outgassing in shadowed craters requires specific, unlikely geometry. Thermal lag can only sustain outgassing for a few hours, not the days or weeks needed to explain these jets. Furthermore, for this model to produce the observed columnation, the geometry has to be exquisitely specific. The crater walls have to be just the right height and angle, the ice deposits positioned precisely, the rotation axis aligned in a particular way. The probability of having multiple craters, all with the perfect geometry to produce multiple, perfectly straight jets, starts to look contrived. The crater model is the strongest natural explanation, and it deserves serious consideration. But it has significant weaknesses. It is one possibility, neither proven nor eliminated, occupying the uncertain space where science operates before definitive answers emerge. The second natural explanation shifts the focus from gas to solid debris. Perhaps what we're seeing is not gas jets at all, but trails of fragments, chunks of material ejected from the nucleus that are themselves sublimating as they travel outward. Comets do fragment. They break apart under tidal stress, thermal stress, or rotational stress. If 3I Atlas has broken into multiple pieces, or is actively shedding large fragments, those fragments could leave visible, linear trails as they evaporate and drag smaller debris with them. From a distance, especially in stacked images, these trails could look like fixed jets extending in precise directions. The apparent stability could be explained if fragments were ejected only during specific rotation phases, so multiple trails all point in similar directions. This explanation has precedent. Comet 73P Schwarzmann-Wachmann 3 famously broke into dozens of pieces, each with its own tail. Comet Shoemaker-Levy 9 was torn into a string of fragments before its spectacular collision with Jupiter. Fragmentation is normal cometary behaviour. But here is where this explanation runs into trouble. Recent observations from powerful telescopes like the Nordic Optical Telescope show that the nucleus of 3I Atlas appears to be intact. There is no obvious evidence of major fragmentation. No multiple distinct cores are visible. The object looks like a single nucleus, not a cloud of debris. If widespread fragmentation had occurred, we would expect to see it by now. Moreover, the physics of fragment trails introduces its own problems. To produce jets extending over 1 million kilometers, you would need substantial, sustained mass loss. Some analysts, working from amateur photometry, have argued that maintaining the observed jets through fragment sublimation would require enormous mass loss rates, potentially more mass than a small nucleus could plausibly provide without completely disintegrating. Where is all this material coming from? And why hasn't the nucleus visibly shrunk or broken apart? The fragmentation hypothesis cannot be dismissed entirely. Parts of what we're seeing might be fragment trails, but as a complete explanation for the fixed, columnated jets, it leaves significant gaps. It explains some features while creating new, equally puzzling questions. We are running out of simple natural explanations, and that should make us nervous, because the alternative explanations are anything but simple. Now we arrive at the hypothesis that changes everything. The possibility that sounds like science fiction, but is being discussed in peer-reviewed contexts by serious scientists. What if the jets are not natural at all? What if 3I Atlas is not a comet, but an engineered object, a spacecraft or a probe? And what we are observing are not sublimation-driven gas flows, but controlled thruster systems maintaining orientation and trajectory through interstellar space. Avi Loeb, the Harvard astrophysicist who championed the artificial hypothesis for Oumuamua, has explicitly raised this possibility for 3I Atlas, and this time the evidence is harder to dismiss. Going the central argument is simple and devastating. If an object rotates but its jets remain fixed relative to inertial space, not rotating with the surface, then something is actively compensating for that rotation. Natural processes don't do this. Gas vents fixed to a rotating surface trace spirals, but attitude control thrusters on a spacecraft can fire in precise directions regardless of the craft's rotation, maintaining fixed orientations relative to external reference frames. This is not exotic technology. We do this with our own satellites and space probes routinely. Reaction control systems use small jets of gas to adjust orientation, to point antennas toward Earth or solar panels toward the Sun. Imagine 3I Atlas as a cylindrical or ellipsoidal probe, perhaps encased in a layer of ice that serves as both radiation shielding and camouflage. Beneath that ice layer, embedded flush with the surface, are thrust nozzles. The probe rotates for stability during its long journey, but its navigation system knows the current orientation. It knows which direction it needs to thrust to maintain course or make corrections. So it fires the thrusters only when the nozzles are pointing in the correct direction relative to external space. The result? Jets that appear fixed in inertial coordinates, straight lines pointing in specific directions, while the surface beneath them spins freely. This model elegantly explains the observations. It explains why the jets don't spiral. It explains their columnation and fixed orientation. It even explains some of the other anomalies. The non-gravitational acceleration becomes deliberate course correction, not random outgassing. The unusual composition might reflect an engineered propellant. The polarimetry anomalies could result from artificial dust or exhaust particles. Loeb has suggested the exhaust velocity of such thrusters would be much higher than 400 meters per second. Chemical rockets achieve several kilometers per second, ion drives tens of kilometers per second. This higher velocity would mean the gas travels the million-kilometer distance in a much shorter time, drastically reducing the number of rotations during transit and neatly solving the unblurring mystery. It would also mean far less propellant is needed, solving the mass loss problem that plagues the natural explanations. Remember that we have sent our own probes into interstellar space. Voyager 1 and 2, Pioneer 10 and 11, New Horizons, they are all out there. If we can do it with 1970s and 2000s technology, why couldn't a more advanced civilization do it better? Why wouldn't they use disguises, coating their probes in ice to look like natural objects, avoiding detection until they are deep inside a target system? The criticism, of course, is that this assumes alien technology without a smoking gun. We have no spectra of artificial materials, no thermal signatures of machinery, no radio signals. All we have are anomalies. When does an accumulation of things we cannot explain naturally become positive evidence for something artificial? This is the heart of the debate, and it cannot be resolved by observations alone. It requires judgment, weighing probabilities, and deciding how much weirdness is too much weirdness to chalk up to nature's diversity. If this sounds familiar, it should. We have been here before, though not quite like this. In 2017, the first confirmed interstellar visitor, Oumuamua, streaked through our solar system. It was immediately strange, an elongated object tumbling end over end with no visible coma or tail, yet it exhibited non-gravitational acceleration. Avi Loeb proposed then that it might be artificial, perhaps a light sail. The idea was met with intense skepticism. Natural explanations were offered. Maybe it was outgassing hydrogen. Maybe it was a nitrogen iceberg. The debate raged and remains unresolved because Oumuamua is gone, accelerating back into the void beyond the reach of our telescopes. 3 Atlas is different in key ways. Where Oumuamua showed no visible cometary activity, 3I Atlas displays prominent jets and a substantial coma. Where Oumuamua was observed only briefly, 3I Atlas has been tracked for over a year, providing a wealth of data. The artificial hypothesis for Oumuamua rested largely on what we didn't see, the absence of expected natural features. The artificial hypothesis for 3I Atlas rests on what we do see, the presence of features that natural processes struggle to explain. This is a stronger position scientifically. Propelled from Oumuamua is that the scientific community is now primed for this conversation in a way it wasn't before 2017. The artificial hypothesis is no longer immediately laughable. It has precedent. peer-reviewed papers, and institutional discussions. NASA has funded studies on technosignatures. This cultural shift matters. It means 3I Atlas can be evaluated more objectively. We have had our first conversation about interstellar artifacts. This might be our second, and we might be better at it this time. When anomalies accumulate, when oddities stack higher and higher, at some point, probability demands attention. Let's talk about the coincidences surrounding 3I Atlas, because individually they might mean nothing, but collectively they form a pattern that deserves scrutiny. This object did not arrive randomly. Its trajectory brought it through the inner solar system on a path that passed relatively close to multiple planets: Mars, Venus, Jupiter. For an object on a random hyperbolic orbit from interstellar space, threading the needle past multiple planetary targets seems statistically noteworthy. Then there is the extreme carbon dioxide to water ratio. Carbon dioxide-dominated comets are rare, even in our own solar system. For an interstellar visitor to show such extreme chemistry suggests formation in an environment significantly different from typical stellar nurseries, another specific condition that reduces the probability this is a random chunk of ice. Balloon's imagery from Gray and Bernoulli adds another layer: dust with unprecedented polarization properties, suggesting grain structures unlike anything we have ever seen in any comet, asteroid, or interplanetary dust sample. We're not talking about unusual, we are talking about unique. And true uniqueness is rare in nature. Engineered uniqueness, by contrast, is expected. Turbulence now add the trajectory alignments, the orientation of the orbit, the timing of its closest approach to the Sun. Some observers have noted patterns that seem too convenient, too optimized. If you wanted to design a probe trajectory through a solar system to maximize planetary observations, you would choose parameters that look a lot like this. What looks suspicious might be exactly what deliberate design would produce. The proper way to evaluate this is through Bayesian reasoning, updating our prior beliefs based on accumulating evidence. Start with a very low prior probability that any given interstellar object is artificial. But each anomaly, each feature that is better explained by an artificial origin, should update that probability upward. If the probability that a natural object displays all 12 anomalies is 1 in a million, and the probability that an artificial object displays them is 1 in 10, then even starting from a very low prior, the posterior probability shifts dramatically toward artificial. This is not proof. This is rational adjustment of beliefs in the light of evidence, and the evidence, while circumstantial, is substantial. But we must also guard against confirmation bias. We are storytellers, and stories about alien probes are more compelling than stories about weird ice chunks. We need independent verification. We need testable predictions. Until then, the statistical coincidences are suggestive, provocative, but not conclusive. They shift the conversation without settling it. Now let's steelman the skeptics because they have legitimate points, and ignoring them would be intellectually dishonest. The strongest criticism is that we are observing artifacts of imaging and interpretation, not physical reality. Keyboard long exposure images are not raw data. They are processed, combined, and enhanced to bring out faint features. That processing involves choices about alignment, stacking algorithms, background subtraction, and contrast enhancement. Different choices produce different results. Could the appearance of straight, fixed jets be an artifact of how these images were created? Consider the observational conditions. These images were taken from ground-based telescopes, often during twilight, with significant atmospheric distortion. Exposure times are long, meaning any motion blurs the image. Stacking requires choosing what to track, the stars or the comet. Different tracking choices can create apparent streaks or jets where none physically exist. Skeptics point to history. The canals of Mars, meticulously mapped by astronomers like Percival Lowell in the late 1800s, turned out to be optical illusions, a combination of poor seeing and human pattern recognition. Could the jets of 3I Atlas be a modern equivalent? There is also the plasma physics argument. Perhaps the observed jets are not neutral gas, but ionized plasma. Ion tails, shaped by the solar wind's magnetic fields, can appear straight and maintain fixed orientations relative to the Sun, regardless of nucleus rotation. This is a plausible natural explanation. However, the November 2012 March 8th images show jets in multiple directions, not just away from the Sun, which complicates this explanation. Spectroscopy could test this, but the data needed may not yet exist. Then there are the complex thermophysical models. Several papers have presented simulations of 3I Atlas using conventional comet physics, and by carefully tuning parameters, the distribution of active areas, the rotation set, they can reproduce some of the observed non-gravitational acceleration. The problem is that with enough free parameters, you can fit almost any dataset. That doesn't mean the model is correct, it means it's flexible. A model that requires very specific, unlikely conditions to work is not necessarily a strong model. Finally, there is the absence of a smoking gun. No radio transmissions have been detected despite targeted SETI searches. No laser pulses. The thermal emission spectrum looks consistent with a sun-warm surface, not machinery. The visible spectrum shows known molecules, not exotic propellants. If this is a probe, it is either inactive, deliberately silent, or using technology we cannot recognize. Each of those possibilities preserves the hypothesis, but makes it harder to test. An untestable hypothesis is not useful science. The skeptics are not wrong to demand more evidence. Extraordinary claims require extraordinary proof, but absence of proof is not proof of absence. What we have is a collection of observations that strain natural explanations without definitively confirming artificial ones. This is an uncomfortable but necessary place for science. It means we need more data, better models, and an honest assessment of what we do and do not know. Confine this thread to its conclusion. Suppose for a moment that the artificial hypothesis is correct. Suppose 3I Atlas is indeed an engineered object, a probe sent by a civilization to explore our solar system. What would that mean? Kind of object it might be. It is most likely a reconnaissance probe, an automated explorer sent to gather data. We do this ourselves. A more advanced civilization would design probes that could navigate autonomously, make course corrections, and operate for centuries. Or perhaps it is defunct, a ghost ship sailing through systems long after its creators have ceased to exist. The scientific and philosophical implications would cascade outward. Astrobiology would have its first definitive proof of extraterrestrial technology. SETI would shift from radio astronomy to object tracking. Our models of how common intelligence is in the galaxy would need drastic updating. The existence of even one probe suggests others. It suggests the galaxy might be more crowded, more active, more monitored than we assumed. The questions become profound and unsettling. Who made it? How far did it travel? How long has it been traveling? The civilization that launched it might be long extinct. We could be examining the work of ghosts. If this is reconnaissance, what are they looking for? Are we being catalogued? The thought is simultaneously thrilling and terrifying. There is also the question of response. Do we attempt communication? Do we try to intercept it? 3I Atlas is moving fast on a hyperbolic trajectory. Any intercept mission with current technology is nearly impossible. We would have missed our chance. Or perhaps missing the chance is safer. Revealing our presence to an unknown civilization could be a risk we should not take lightly. If confirmed, 3I Atlas would become one of the most important objects ever observed. It would trigger an unprecedented global scientific campaign to gather every possible piece of data. But confirmation is the challenge. How do you prove something is artificial without seeing the serial numbers? The standard of proof would be extraordinarily high. We are not there yet. We have anomalies, not answers. But the mere act of seriously asking the question has already changed us. While we ponder whether 3I Atlas might be artificial, another form of intelligence is revolutionizing how we explore the cosmos. Artificial intelligence. In 2025, researchers published a breakthrough demonstrating how machine learning algorithms can detect exoplanets in noisy data with unprecedented accuracy. The study focused on data from the Kepler Space Telescope. Kepler monitored the brightness of over 150,000 stars, generating billions of measurements. Finding the tiny periodic dips caused by transiting planets was a monumental task of signal-to-noise analysis. Traditional methods involved automated algorithms and human inspection, a labor-intensive process that was almost certainly missing subtle or unusual planets. Machine learning changed the game. Researchers trained models like random forest classifiers on known data. The algorithms learned to recognize the characteristic signature of a planetary transit, incorporating subtleties that humans or simple algorithms could not articulate. The best models achieved over 99% accuracy, and they could process millions of light curves in a fraction of the time it would take a human team. This is a fundamental shift. It means we can find planets faster, including rare and unusual ones that don't fit the standard mold. But there is a deeper parallel here. Machine learning excels at finding anomalies, patterns that deviate from expectations. This is exactly what we need for technosignature searches. Imagine training an AI on all the data we have from natural comets and asteroids. The model learns what normal looks like. Then you point it at a new object like 3I Atlas. Its unprecedented polarization, extreme chemistry, non-gravitational acceleration, and unblurred jets would make it light up the system as a massive anomaly, triggering intensive follow-up. The same approach could revolutionize SETI. Instead of just looking for signals we expect, like narrowband radio transmissions, AI could be trained on natural astrophysical radio sources and flag anything that doesn't fit. We could start finding signals we didn't know to look for. There's a poetic symmetry here. If 3I Atlas is a probe, it might itself be running sophisticated AI to analyze our solar system. An alien artificial intelligence, autonomously making decisions about what to observe, recognizing Earth as an anomaly worthy of study. We could be watching alien AI at work, just as our own AI helps us study the universe. Two forms of intelligence, one biological and one synthetic, meeting across the void, both relying on the same fundamental logic of pattern recognition and data analysis. While astronomers watch the skies for interstellar visitors, physicists are hunting for something far stranger in laboratories deep underground: dark matter. This invisible substance makes up about 85% of the matter in the universe, but it has never been directly detected. We know it's there from its gravitational effects, but it has never interacted with our detectors in a confirmed way. For decades, the hunt has focused on WIMPs, weakly interacting massive particles. Enormous, sensitive detectors filled with liquid xenon have been built in deep underground caverns, waiting for the rare collision between a dark matter particle and a xenon nucleus. Despite exquisite sensitivity, they have found nothing. In 2025, a breakthrough in detection technology offered a new path. Researchers developed ultra-sensitive superconducting nanowire single-photon detectors, SNSPDs. These devices, cooled to near absolute zero, are so sensitive they can detect individual photons. The new approach targets ultra-light dark matter particles, far lighter than WIMPs, which might produce single, faint photons when they interact with matter. This opens up a whole new parameter space in the hunt, a fresh frontier after years of null results. The philosophical connection to 3I Atlas is subtle but real. Both represent searches for things that do not fit our standard models. Dark matter challenges our understanding of what matter is. An artificial interstellar object challenges our understanding of what natural means in astronomy. Both require us to question fundamental assumptions and consider exotic possibilities. Both demonstrate how progress comes from building new instruments that can see what was previously invisible. There is even a wilder speculation. If dark matter particles exist and interact, could an advanced civilization learn to manipulate them? Could they use dark matter for propulsion or as an energy source? If 3I Atlas uses exotic propulsion, could it involve physics beyond our current understanding, perhaps including dark matter interactions. This is pure, untethered speculation, but it illustrates how discoveries in one field can radically expand our sense of what is possible in another. The James Webb Space Telescope continues to rewrite textbooks. In 2025, one of its most stunning discoveries was the direct image of TWA-7b, a Saturn-mass exoplanet orbiting a young star just 32 light-years away. Direct imaging is incredibly difficult, like photographing a firefly next to a searchlight, but JWST did it. The images showed the planet sitting within a complex debris disk, not one ring, but 3 distinct concentric bands of dust and rock, with gaps likely carved by unseen planets. TWA-7b itself appears to be sculpting its part of the disk. This is a snapshot of a planetary system in the process of formation, a dynamic construction site where planets are building and shaping their environment. Crimson matters for 3I Atlas because this is where comets come from. Comets are the leftover building blocks, the icy debris from planetary formation. When we see a young system like TWA-7, we are seeing the factory where objects like 3I Atlas are forged. Some fraction of comets formed in such disks are inevitably ejected by gravitational interactions, becoming interstellar wanderers. Plumbing, but this also deepens the speculation. If comets naturally form in debris disks, and if civilizations arise in some of these systems, could they deliberately place probes in their own debris disks, disguising them as natural comets? A probe coated in ice would be visually identical. Given a gentle push, it would be ejected by planetary interactions along with the natural comets, its trajectory appearing entirely normal. It would be the perfect camouflage, hiding in plain sight among thousands of similar objects. If this strategy is used, then some small fraction of the interstellar objects passing through our system might be artificial. Not all, perhaps not even most, but some. And 3I Atlas could be one of them. JWST is teaching us what normal looks like across hundreds of systems. It is building the statistical foundation we need to identify true outliers. You cannot recognize an anomaly without knowing the baseline. With every new system JWST images, our baseline improves, and our ability to say whether 3I Atlas is within the realm of natural possibility or a genuine outlier becomes more precise. While we search for signals from potential probes, humanity is developing communication technologies that would seem like magic to the past. In 2025, China's quantum microsatellite, Jinan-1, achieved a major milestone: real-time quantum key distribution between a satellite and ground stations on different continents. Quantum key distribution uses the laws of quantum mechanics to guarantee secure communication. Information is encoded in the quantum states of individual photons. Any attempt to eavesdrop disturbs these states in a detectable way, making the interception provably impossible. Jinan-1 demonstrated this from low Earth orbit, maintaining quantum coherence through hundreds of kilometers of atmosphere. This is a fundamental shift in secure communication, paving the way for a quantum internet. The connection to 3I Atlas is speculative but profound. If we are developing quantum communication, advanced civilizations certainly have. A probe like 3I Atlas might use quantum transmissions to report home, signals that would appear as random noise to us, completely indistinguishable from natural background radiation, unless we knew the exact quantum protocol to decode them. This raises a troubling possibility for SETI. The window during which civilizations broadcast easily detectable radio signals might be very brief. Advanced technology might use efficient, undetectable quantum signals. We could be immersed in alien communications right now and be utterly deaf to them. Stabilized offers new search strategies. Quantum states are fragile. They decohere in warm, noisy environments. A natural comet should show no quantum coherence. But if 3I Atlas contains superconducting circuits or other quantum devices, they might maintain coherence, producing a signature we could potentially detect with the right instruments. As our own technology advances, it gives us new eyes to see what was previously invisible. The discovery and intense scrutiny of 3I Atlas represent a turning point. Before Oumuamua in 2017, interstellar visitors were theoretical. Now we know they are regular, if infrequent, guests. As our telescope networks and detection algorithms improve, we will find more. This has profound implications for planetary defense. Planetary defense programs, designed to track near-Earth asteroids, must now expand their scope to include interstellar objects. These visitors arrive with little warning on non-repeating trajectories. We need faster early warning systems, ready to deploy characterization protocols, and international coordination to study them before they escape. The ethical questions also become urgent. If we confirm an object is artificial, what do we do? Attempt to communicate? Intercept it? Observe quietly? We have no international protocols for this. The capability to intercept such a fast-moving object is beyond us now, but we must prepare. Porcelain may be proactive preparation, placing observational assets in the outer solar system to detect incoming visitors years in advance, giving us time to mobilize. The potential payoff, contact with alien intelligence, dwarfs the cost. Whether 3i Atlas is natural or artificial, it has already changed us. It has pushed us to refine our models, develop new techniques, and seriously consider the possibility of alien technology. The taboo has weakened. We now know how to ask the right questions. The universe is vast and ancient. We have just begun to watch it closely. 3i Atlas may be a footnote or the most important discovery of the century. We don't know yet. But as it continues its journey outward, back into the interstellar dark, we watch, we measure, we debate, and we wonder. Because wondering is what drives discovery, and discovery is what transforms wonder into knowledge. The jets remain, straight and unyielding, fixed against the rotation that should smear them. 12 anomalies stack high. We are left in the most uncomfortable and exciting place science can be, suspended between certainty and ignorance, knowing something profound might be happening, but unable to prove it. This is where great questions live, and in the asking, we have expanded our sense of what is possible, taking one more step toward whatever future awaits us among the stars.